Hello everyone, after a very long time today our topic is very interesting, and our topic is magnetic field due to a current carrying solenoid. But before discussing this topic, let's first understand what is basically a solenoid is. So solenoid is basically a wire wound in the form of spring or helix is known as solenoid, and whenever we passing a current through that wire which is wound in the form of spring or helix, it produces its own magnetic field and becomes an electromagnet, and the behavior of this solenoid is just like an ordinary bar magnet which having north and south poles. So the magnetic field lines coming out from side behaves as a north pole, while the other side of the solenoid behaves as a south pole. You see here the shape of the magnetic field lines due to a current carrying solenoid. Notice that the magnetic field inside the solenoid is much stronger and uniform as compared to the outside, and it is also well understood that the magnetic field outside the solenoid is very much weaker as compared to the magnetic field inside the solenoid. Therefore, for our purpose for solving our different problems related to the solenoid, we can sometimes ignore the outside magnetic field, or we can say that it can be neglected compared to the inside field because it is uniform inside and also much stronger. So that's why we can understood the solenoid like this. Let's suppose this solenoid has length L, and we are interested in order to find out what is the magnetic field due to this solenoid is. So our main problem or our topic is the magnetic field due to this current carrying solenoid. So how we can find the magnetic field due to this current carrying solenoid? By using Ampere's law. So according to Ampere's circuit law, the magnetic induction over an Amperian loop is equal to the mu naught times the total current enclosed by that loop. So with the help of this law, we can easily find out the magnetic field due to this current carrying solenoid. So as we know that for solving our problem, we can draw an Amperian loop. So how we can draw that Amperian loop? Let's simplify this diagram as well. We know that for solenoid, we can use right hand rule for magnetic field representation as well as for current. So hold your right hand in such a way that the curl finger will represent the current, while the thumb represent the direction of magnetic field. So in this case, the current is anti-clockwise, so the magnetic field lines will be from left to right in this direction, and these dotted here in this diagram basically shows that the current is coming out of the page here, and these crosses shows that the current is going inward towards the page. So the shape of the magnetic field line is like this. As we know that inside the solenoid, the magnetic field lines are equally spaced parallel, and magnetic field is stronger and uniform. So therefore we can draw only this section of solenoid for simplicity. And now draw the Amperian loop A, B, C, D, A. Now further we can divide this Amperian loop into 4 elements, and the first one element is AB, which having length L1, the other one length Amperian loop length element is L2, the other one is L3, and the other one is L4. So this is the Amperian loop, and these are the magnetic field lines. Now according to Ampere law, B dot del L is equal to mu naught Ni. So here we see that basically the magnetic field and the length element L1 is parallel because the magnetic field is parallel to the axis of the solenoid here. So L1 and magnetic field is parallel. So therefore by expanding left side of the Ampere's law, we have 4 sections. So B dot del L1 B dot del L2, B dot del L3 and B dot del L4. We have 4 sections. Now the section number 1 L1, we already stated that basically magnetic field is parallel to L1, so B dot del L1 plus L2. You people see that basically length element L2 is at right angle, means at 90 degree, so therefore theta is here 90 degree, and L3 is outside the magnetic field, so we know that there is no magnetic field, so outside the magnetic field term this one is 0. And we know that this here is the dot product, so dot product mean cos theta, and cos 90 is equal to 0, so this one term also goes to 0. And L4 we know that it is also at right angle to the magnetic field, so therefore cos 90 is again 0. Only this term survive because theta is equal to 0, and we know that cos 0 is equal to 1, so cos 0 is equal to 1, only BL1 left, so therefore this equation becomes like this: BL1 is equal to mu naught I. Now we know that here are n number of turns, so for n number of turns BL1 is equal to n mu naught I. So this is our final equation for this solenoid. But as we know that basically there is a small n which is defined as the total number of turns per unit total length. So by simplifying this equation, number of turn n becomes small n multiplied by L. So it means that we can replace this capital N by small n multiplied by L. So this equation becomes like this by replacing n as a NL. So when we replace that, we know that to the left side there is L1 and to the right side there is also L1, so L1 and L1 cancel out. So after simplification we get equation B is equal to mu naught Ni, or B is equal to n mu naught I, which is basically the magnetic field due to current carrying solenoid, which means that the magnetic field due to current carrying solenoid depends upon the number of turns per unit length, the magnetic permeability and the current passing through the solenoid. So this is our final equation, and we can solve different problems with the help of this final equation, which is a very basic and fundamental equation of solenoid. After this we can also find the magnetic field for toroid as well. So keep watching our videos. Further videos will be more interesting. I hope you like this video. Please subscribe my channel as well if you like these videos, because upcoming videos are more explanatory and more topic will be discussed in more interesting way. Thanks for your time.